a ternary diagram like this. And this is the U.S. energy mix from 1845 through to about 2005. But since 2005 to today, it's slightly changed, but not dramatically from that point. And what you see is a very interesting transition from predominantly renewables, which was at that point in time wood, right? Over to this corner, and something happened here in the early 1900s that drove up that direction. Started in Texas, by the way. Oil and cars, right? That's the other major transition on that front. And then we get to the top and we're kind of playing around. But I think fundamentally what we have then is the question of which direction do we want to go as we think about actually mindfully crafting energy policy. And that's a very important point of kind of departure as we think about what historically has happened on the resource side or on the use side. And now we have lots of options at our fingertips. We have a lot of technology. We actually are economically very prosperous. Domestically, as I think about that, we can have a conversation about what this means for energy and development. And we have real conscious choice of what that means. And I'll talk about what some of those complexities are toward the end of it. I always go back to this actually quite old slide. This comes back from, I think, AR3, the Assessment Report 3, where we were looking at scenarios of total world primary power. So world energy supply, this is now in terawatts rather than in joules or exajoules, et cetera, back then. And then what those scenarios would look like under different mitigation pathways. So again, this is in ppm equivalents. And I think there are two interesting points to think about on this without belaboring it. One is that if world population continues to grow and demand grows as it had in the past, that the world demand for energy, expressed here in terawatts, is actually anticipated to grow fourfold, something like that. And so can one imagine an energy system which is actually 4 times larger than it was, well, let's say now in 1990, but let's say twice as large as it is today? That's actually a fairly large challenge. And the second is that if it grew at that rate or to that level and it maintained its carbon intensity, we would be nowhere near any of those mitigation pathways. And so I think we understand that pretty well these days, which is we have to decarbonize the energy system. We also have to think about very dramatically energy efficiency, i.e. reducing the energy intensity of our economies. And I presume or hope that you're familiar with the fact that the US economy is twice to 4 times as energy intensive as most other, or many other, not all of them, developed country economies. And let's then not forget about the roughly 2 billion people in the world who still don't have power. It was 2 billion people when I started really working in this space a couple of decades ago. In all of that economic growth over the last couple of decades, in the population expansion, in the economic prosperity, there's still 2 billion people without access to modern energy, roughly 1 billion people without access to electricity. And yet, at the UN level, at the international negotiation level, in what's called the Millennium Development Goals, sorry, there's a typo in the top there. It should be MDGs, not MGDs. Energy isn't expressed explicitly in any one of them, but energy is at the core, or I would argue energy is at the core of all of them. And that's a really important point to think about when a traditional economist has thought through what development looks like. It's, well, GDP drives energy growth. Well, maybe that equation actually is different. And maybe we should think about how does energy, and particularly modern energy, enable economic productivity and economic growth in a very different way. So, someone asked me a little bit before kind of, why did I transition from a PhD in analytic chemistry then add an MBA, and now do what I do in terms of national academies and all sorts of other interesting things. And this slide is kind of the essence of that, and it's really in the title of it, which actually reflects the philosophy of a gentleman named Bob Craig, who actually is the founder of the Keystone Center. He was actually the founding executive director of the Aspen Institute. He was a member of the 1953 American expedition to K2. He was a climber. And he fundamentally believed in data and facts, and then I'll call it informed discourse and dialogue to get to decisions. In my world, because I was trained as a scientist, I think fundamentally that credible, objective data and analysis, i.e. science, can be a really good tool for decision making. It doesn't have to be just policy making, but really decision making. It's clearly much more, I'll call it straightforward in the business world, where straightforward economics move forward and drive a lot of decisions. But in the public policy domain, I think it's actually very, very important. And to that end, in terms of what we do in energy and what you all do in energy, making better scientifically informed forecasts, better knowledge, better data available to decision makers, I think, is absolutely critical. And then on the flip side, when we're dealing with climate, how accurate are the climate models? They're actually incredibly accurate today relative to even 20 or 10 years ago. And people would argue that they're much more accurate, in fact, than our economic models. And we can have a really interesting Q&A session about the difference between physics-based models and economics models. But we'll go on that. So I think we're here to talk about energy and the opportunities and challenges. So this slide kind of compiles together a bunch of different pieces around transforming from today's energy system to a sustainable energy system. And sustainable, I'll reflect back to the Brundtland Commission definition. So that includes all of the aspects of really prudently taking care of, leading, being a good steward of our environment for many generations to come. And at the bottom, it talks about the services, or at least one layer or interpretation of those services, rather than thinking about delivering an electron or a gallon of gas or things like that. So I'm not going to go through that in all sorts of detail, but I think it's really important to think about that. So how hard is the problem? Well, I'm not sure if this is a glass half full or a glass half empty slide. So this I took from good friends at Deutsche Bank Climate Change Advisors who did this calculation. And you see two graphs on here. One is U.S. labor productivity as a function of time, indexed time. That was 1830 to 1955, which was essentially the core of the Industrial Revolution. And you can see how much that went up, roughly a factor of 10 over blank, 125 years. And that's and then on the left you see the required carbon productivity over about a 50-year time period, 42-year time period, in order to hit a 450 ppm scenario, if I remember exactly the scenario that was put in there. And that shows the challenge in front of us, though I would say one can interpret this as either, oh, that's really hard to do, but one may also interpret it to say, well, the world's changed a lot. We have a lot more technology, we have a lot more economic productivity, and maybe that's not so difficult. But it gives us some sense of historical perspective in terms of what's in front of us. Into a little bit more traditional thinking, this is kind of a classic slide from an NREL perspective. There are lots of opportunities across all of the, quote, key systems, if again you want to think about systems and energy supply into conversion systems, into systems which deliver services. That's the built environment. So I think that is not a picture of one of our NREL campus buildings, but I'll put one up eventually. Electricity, community scale systems. There's a lot of work right now that we're doing, you're doing, I think, on islanding systems, microgrid systems, systems for island nations. A couple of us talked about Hawaii earlier as that going. fuel and transportation systems as it goes forward. So there's not much detail in there, but on this slide, let's just focus in on the power sector. And here I stole a little data. Actually, I didn't steal it. I'm going to use it with attribution from Bloomberg Energy Finance that just put this out. This shows their fossil fuel investment capacity changes from 2010 and then their forecasts with their tools, which are not quite as transparent as I would like them to be, but I'll just use this as a point of departure, where they actually project, interestingly, a decrease in fossil fuel investment and capacity expansion globally now, going forward for the next 20 or so years, and a continued and relatively significant increase in clean energy technologies, which they define here to include hydro and all the traditional renewables plus nuclear. So clean being essentially decarboned for them. They don't have CCS in that world. There are a couple of other interesting reflection points if you don't study this. One is to look at the 2010 and 2013 data, and you'll actually see that in capacity amounts, that actually the new capacity of clean energy technologies and fossil technologies globally was about equal. In fact, it was slightly higher in the renewables and the cleaner side of the equation. That's actually fairly interesting on a capacity side. It's a little less so if you think about the details of the capacity value, the amount of delivered energy out of those systems, because wind and solar systems don't deliver the same number of hours in a year as a coal plant does or as a gas plant does on average. Let's put it that way. So a couple of different thoughts there to think about. And then I'm sure many of you are familiar with what's happened in the U.S. power sector over the last number of years. And there's a couple more years of data out here, but I think this generally gets the trend in terms of increase in renewables, decrease in coal, and increase in gas. And we can have an extensive dialogue about the dynamics of what's happening in the U.S. power sector, given the Clean Power Plan, given EPA rules, given shale gas pricing, given campaigns for coal retirements and state-level policy changes that are happening or have happened and are now kind of into their sunset worlds, et cetera. That will leave for Q&A, but I think it's interesting to bring into the perspective what trends there have been and what's driven those trends. And so there's a lot of dialogue about why has coal retired? Why has gas increased? And there's some fundamental economics there. There's some fundamental policy pieces. There's also, frankly, risk planning, risk and prudent planning, as well as state mandates. And it's a combination of all of that which has driven those changes, not one particular piece. So you all are much closer to this, back to Frank. Well, actually, you're about equally as close to this as NREL is physically. So NREL's very close to the DJ Basin in Colorado and then the Piceance and others. And we work very closely with numbers of colleagues across the natural gas academic space, including some colleagues down here. And you all, or many of you, I say, are familiar with, if you don't research in this area, if not, pay attention to the news locally, et cetera. So this is a slide of lots of words, and I think rather than think through those specifically, I think I'd like to capture the essence of what's happened in the shale revolution with a couple of thoughts about it, which is that I think one of the most interesting reflections is that very few, if any, energy analysts predicted that there was going to be a, quote, revolution. Maybe some saw it coming, but never actually penciled it out in an economic model, never thought through what it might look like in terms of the dynamics of investment in the industry, the impact on the power sector, the impact and the drive on the industrial sector, which have now announced more than 100 new plants, many of them here in Texas, to take advantage of this new coal and new and less expensive coal. I'm sorry, not coal, unconventional gas. But it's not, as it says, a done deal. There's still lots of questions. David Allen and team are very active here. Michael, you're active here. We're active, many others. throughout the nation in terms of really understanding the impacts of shale development, both from a technical standpoint, but also maybe more interesting from, I'll call it the social license to operate standpoint in terms of what's the social acceptance. So Colorado, and I think 6 counties or 6 localities in Colorado and 1 in Texas, is that right? Moved to ban locally fracking. Is that right? Just 1?
One Texas ban, but then others have banned the use of municipal water. So they have
Okay.
some limited bans.
So limited ban of some sort. So this is a complicated slide, but it's one we put together in a report of ours, and then Mark Zobak and I, who's a professor at Stanford, have I'll call it refined it a bit. But it really talks about the risk factors in natural gas development, and that's from fracking or from any other, frankly, supply. It doesn't have to be unconventional, but it tends to be dominated by unconventional, particularly because of the above ground issues that are related to it. And there's a whole complication of pieces, be it from the ecosystem, from the social side in terms of wells, waters, impacts on farming communities, setback laws, which actually were put in place decades ago, well before people ever understood that there was resources underneath communities and schools, and that they required then contiguous ownership of mineral rights, which is a very interesting thing to think about as to whether or not, if that wasn't in place, what would happen. Could people actually step back 2 miles and access those minerals or not, is another question. So there are lots of issues here. Almost every single one of these issues is ripe for a thesis and ongoing work. And there's a lot of research happening right now in it. And it's not solved either on the science side, and it's certainly not solved in the public discourse side of the equation. And that will take some time to evolve. And I think my reflection globally, because I had a conversation with at least one of you about what's happening internationally on this front, is that people outside of the US are watching us intensely. And some are very quick to act and put rules and regulations or moratorium or bans in place. Others are a bit more mindful and prudent about their approach to it, but yet they also aren't living it in real time. And so, for example, you can see a plethora of different approaches throughout Europe on this front, and you can see, I'll call it a cautious optimism in China that's sitting on what's estimated to be the world's largest unconventional resource base right now, but really hasn't yet been developed even really at all. But different geology, certainly different geopolitical context domestically, et cetera. So let me go into a little bit of solution space and see where some solutions might come from. This is just traditional analysis from the Energy Information Agency showing the growth in electricity mix in the US. This is from their most recent forecast that just came out a couple of weeks ago, and it shows kind of a general trend toward moving toward more natural gas and more renewables, mostly at the expense, in this case you can see it, of coal and nuclear. The coal and nuclear come from the policies in place and the economic pressure on coal plants to go, and also there's a history, there's an aging profile, et cetera. Nuclear is really around retirements and the fact that there are very few new builds in the US, and then natural gas is really around pricing and what that looks like, as well as coal driven by state RPSs and existing policy. That's a fairly positive view of the world in terms of changing transitions. It doesn't get you very far in terms of really hitting deep decarbonization goals. So that Clean Power Plan, for example, draft Clean Power Plan rules are not reflected in this because they're not final. What would the non-hydro renewables look like in that case? So if you take just the kind of the clean energy or the renewable-centric perspective on this, you actually see nearly a doubling between 2012 and 2040, and you'd say, wow, that looks pretty positive. So you reflect back to the Bloomberg New Energy forecast and you say, well, that's a good sector to be in. I wonder if, if that's really everything that's there, and how do I have to compete, and what's happening on the cost side. And I'm not going to talk about all the cost reductions that have happened. We can talk about that in Q&A if you want to. I presume you're pretty familiar with it. But what are some other options, and how else might we get to deeper decarbonization in the U.S.? So these are results of studies that we've done at NREL. They use a very detailed traditional economic model called REEDS, the Regional Energy Deployment System model, that models the whole United States in good technical detail. It's about, I'd say today it's, and a couple of actually postdocs and graduated PhDs from here actually are up working on that and doing very well. But it has about, I think, 1.2 million variables in it and has about 200 or 300,000 constraints. At minimum, it runs about 24 hours for the United States, and at maximum, depending on what else you put in, it runs for days. So it breaks up the country into 300 and some odd regions. It solves supply and demand in each region. It actually allows for transport across the whole country, building transmission or restraining it, or complying or not complying with local, state, and regional laws, et cetera. So that's a bit about the tool. It's called REEDS. This is a bit of the outcomes just from looking at 3 scenarios actually with no new policies, but looking at shale gas impacts. And so there's a baseline scenario on the left. There's a scenario in the middle, which is really around low estimated ultimate recovery. That's what EUR stands for. And then there's one on low demand. And, you know, kind of interestingly, this is again back to the story of the unappreciated, shall we say, value of energy efficiency, which is it's always the least cost, first cost resource when you look at it traditionally economically. And I think that there are a couple of folks here that study the human behavioral side of the equation, and many of us are familiar with that if we've rented an apartment and not cared about the electricity bill or the water bill. But we should think about deeply what are the market structural behavioral issues of why we don't choose an efficient pathway, or why we haven't chosen an efficient pathway in the past. And that's very different here than it is in Europe. And I think we should maybe reflect a little bit on that in the Q&A session. There's a very different paradigm in terms of either in Europe or in Japan particularly about individual action that's in support of the common good and a common goal, which is very, very different than the, I'll call it the behavioral aspects and paradigms and perspectives in the US. So I've got 10 minutes to run through a bunch of others. So here are a couple of other scenarios in terms of looking at different options. CCS up here is carbon capture and storage. High EUR means high available gas and low available gas. The interesting piece that I think I want to point out here is that in each of these scenarios, if it works, maybe it doesn't work, okay, I'm not going to use it, is that look at the increase in renewables, and I'll just use the green swath at the top because during the time we did that analysis, it was wind, which was the least cost renewables, which actually went online. And then look at the synergy of that with the natural gas swath, which is kind of the brownish piece in the middle. And what you see is that there's some very nice complementarity. At the front end of any of these scenarios, coal actually reduces quite significantly, gas grows, and renewables continue to grow. And then in any of these going forward, these are all relatively deep decarbonization. You continue to have gas in the system, but then you have also lots of renewables. And so that takes us to another thread of work that we've done, and Michael's participated in a couple of these discussions about the potential synergies between gas and renewables, which could be either at a site, on a campus, or in the system itself. And that warrants deeper and deeper thinking about how do we make that transition or argue for that transition without compromising the long-term sustainable transition of the system. So a little bit of further deeper work in terms of looking at those higher renewable scenarios. So this is a different set of scenarios still with a REEDS model. We looked at a series of high renewable penetrations for the country out to 2050. High renewable meant from 30 to 90%. And so DOE asked us to do this study. It was many years and many millions of dollars and hundreds of researchers involved in it. It's up and available on the NREL website. It was actually published a couple of years ago. We've done some updates on it. And fundamentally, the question that we were asked to answer was, could the U.S. electricity demand, as projected out to 2050, or under different scenarios in 2050, actually be met with the bulk of energy coming from renewables, or renewables providing 30 to 90%? Because we didn't know the answer to that. Most people at that point in time had looked at scenarios of 20, maybe 30%. The Danes were pushing toward 50 or 60. They're now pushing to 100%, but they're in a very unique situation. We can talk about that. So that was the fundamental aspect. Do the wings fall off the plane? Does the system solve? Does the model work? And the answer was yes, at least as far as the first cut analysis that we've done, which again was I'll call it a feasibility study. It's not a deep electrical engineering study. It didn't look at all the contingencies. That the system actually could evolve at least to 80% renewables on a national basis, and that's 80% of energy delivered, so electricity delivered. Here you see some of those results and what that looks like from moving from 30 to 90%, both in capacity as well as delivered electricity. And importantly is to think about, when you're in the weeds, if you're an electrical engineer, is how much of that is variable. And you can see that that's the line over there. So at about 80% it's of total energy coming from renewables, it's a give or take about 40% variable. And so that actually seems to be perhaps manageable, at least as we looked at it at an hourly basis. That's what the mix looks like across the country. A lot of detail on this slide. I would just say, take for granted that every part of the country contributes very significantly to that national mix. Some parts don't quite supply their own demand, and other parts have oversupply, and therefore there's cross-regional trade in this particular scenario where we allowed that trade to work economically. If we restricted that economic trade, you actually build more inside those systems, and you do that at slightly increased cost, but that's relative to the trade-off of whether or not you could build new long-distance transmission in the United States or not. There are a couple of fundamental aspects of what a power system looks like and how it would have to operate in the future if it does incorporate more renewables. And they're listed here. This is the point of ongoing significant amount of research at NREL and with colleagues around the world. You'll see a list of them here. There's a lot of innovation that I'll talk about toward the end, which I think helps address many of these issues in terms of flexibility broadly. And we can talk about that in the Q&A session. Well, I might skip through this. These are dispatch examples of how the system operates either at peak or at off-peak under different scenarios, and they frankly show what a system operator's worst nightmare looks like under an 80% scenario. If you look at the right-hand side of the graph up there, you can see kind of nice alignment with demand, which is the black curve at the top in the peak system, but in the off-peak system, what you see is oversupply a lot and just what looks like relative chaos from the back of the room. If I slide through these to different scenarios which have different technology profiles, you can see it essentially stays about the same in terms of qualitative aspects, but the key aspect is that the thermal generators change their profiles from what's on the left-hand side to the right-hand side. They go from essentially relatively uniform profiles, at least particularly for coal, and I'll call it relatively predictable for the gas profiles, into much more flexible systems on the right-hand side. And the question then is how are those systems operated? What are the economics of them? What are the environmental footprints of them? And maybe more importantly, what are the market structures which allow those systems to operate financially viably in that type of environment? And we can talk about that in the Q&A as well. Let me keep going. I'm going to skip through that. So this is a summary table, and I wanted to bring this up without going through the other slides in some detail, because it shows also some of the scenarios that we looked at that weren't economically optimum in that kind of traditional manner. That economic optimum, this 80% incremental technology improvement, that's what that ITI stands for, allows us to build transmission as we need to in the economic optimum way. And you can see that then we can either constrain that transmission build, we can constrain flexibility in the system, we can reduce the amount of renewable resources that are available to the system, or we can project really high demand. And in any of those particular situations, the system's still solved, per se, i.e. we could find a reasonable solution going forward, but there are trade-offs. There are always trade-offs within this, and the trade-offs, this is more information to inform that trade space and those decisions in terms of whether or not you build high transmission or you develop local resources. And the economics of those trade-offs would change if we'd modeled it today than what we did 2 years ago, because frankly, solar and batteries have changed dramatically, and maybe microturbines and fuel cells will as well. And that will continue to evolve, and you need to continue to kind of keep up the science and the analysis in order to inform those decision-making processes. I think one of the interesting takeaways as well is if you look at the storage requirement here, the kind of, I guess one of the key things I always like to remind people of is that variable renewables do not require one-to-one backup, if you want to use old language for that. There's a myth in the system that says, oh, if I have a gigawatt of wind, I need a gigawatt of flexible gas. And so the US system is give or take 1,000 gigawatts. It has give or take 20 gigawatts of storage on it right now, roughly, if I remember the number correctly. And that system goes in this world to, if you remember the numbers from the other slide, 1,500 gigawatts or so. And we build more storage, but in an 80%, in a solution that's 80% renewables, you don't have 800 gigawatts of storage because you've got more flexibility, you've got regional balancing, you've got demand response, you've got electric vehicles in the system, et cetera. So that myth of, well, I need gas if I have wind, really is a myth. All right, so let me try to wrap up with, I think, some reflections on where we're at today and where the real opportunities lie outside of just providing, I'll call them traditionally oriented solutions on the production side and on the supply side. And this is old numbers, but the numbers really don't matter here. It's the trends. How many people in here have a smartphone? Oh, wait, how many people don't have a smartphone? Oh, awesome. We still have 3. Okay. That's good. How many people do not have an internet account? All right, that's good too. So, how many people use social media or don't use social media? Oh. Holdouts. Interesting. The fact is that IT, sensors, the Internet of Things, if you want to use that buzzword, is really an opportunity around changing our energy paradigm that we haven't yet appreciated or we're just starting to appreciate. Some of you are working with bigger data sets. Some of you are working with, I'll call it, distributed intelligence. But those are only the front end of thinking about the opportunity in reinvention of the energy space and the climate space and frankly our economic paradigm. And so I offer some thoughts here, and how many of you have ever used a car sharing service? Zipcar, Lyft, or Uber? Okay. Some, not many. How many have used Airbnb? Couple, all right, not bad. So what do those business models represent? Those business models represent a change in the asset utilization and a change in the economic paradigm. And frankly, if we think about that from our energy perspective, they might offer us, particularly in transport where we don't have so many solutions, a really interesting opportunity to change the way the world looks going forward and frankly our energy footprint. So I promised you a picture of one of our buildings. This is the research support facility on the upper left. That's a Class A net zero energy office building where I work and many others who are there, like almost 1,300 people, I think. It's net zero energy once we have photovoltaics on the roof and the parking garages, and it was built at essentially zero marginal cost to building a traditional building that had a traditional air conditioning system and a traditional heating system in it. And every detail is up on the website. I encourage you to look at it. It was done that way as an example for others to replicate. And then you've got other wild and not so crazy ideas, but interesting ideas about how to think differently about the energy system and how to really invent our way into the future technologically, but also, as I said earlier, about business models and decision making. So this whole idea of asset utilization, cars have a really poor utilization rate. See a number of people think about that. Different than buses, different than trains, different than airplanes, different than ships. Your house, really terrible utilization rate, particularly if you calculate on a per square foot basis. A lot of opportunity there if you want to share rooms and other things like that. The other pieces that are actually changing that I think, particularly for those that are thinking about going out into an entrepreneurial space, is raising money, using money, business models. So I put this one piece up here of pension funds and traditional financial value chains. I know at least one person in Bruins Group's looking at the venture capital and strategic partnership investment community, to crowdfunding. And crowdfunding's not just for US-based businesses, but think about the B Corps. I don't know if you know about, anybody know about B Corps? A couple folks, okay, you should talk at the reception or whatever. And think about those folks that are investing in B Corps or funding B Corps or founding B Corps and energy access. And I know dozens of people who have founded B Corps in order to provide clean energy, economic development-based services in developing countries. And it's this crowdfunding approach that not only will bring energy access to them, but new business models here as well, that I think is really important. So, a couple other just quick thoughts. You're probably familiar with Michael Porter's 5 forces. So these are Doug Arent's different landscape forces. Haven't put it in a book yet, and I don't think I'd get the publication that he would. But I would say that this is a framework, at least that helps me think about how do we drive change into the future and what do we need in terms of hitting those carbon decarbonization goals? How do we invest in new businesses, invent new businesses? How do we take advantage of the IT infrastructure and data assets? And how do we think about hyper efficient or just at least efficient or more efficient use of assets? So I'm going to skip that. I'm going to put that one up in lieu of time, and I want to come back to just the policy dialogue. And so this is I'll call it a decision scientist diagram around policies which doesn't make any sense to most people whatsoever. So what does it reflect? It reflects the different weighting, or I'll call it cartoonishly, the different weighting of different institutions about things that they may or may not care about in terms of making decisions. And so here you see, I don't know, a dozen or so attributes or criteria that people might think about, right? Resiliency, mission, economic prosperity, the environment, globally or locally, water, food, et cetera, et cetera. Many of those things on that front diagram. But every personal decision complex is unique, and every institutional one, I would say, is nominally unique. And so it's hard to come to a decision and a policy environment with one single framework in mind. And this is why the decision making and policy making is so difficult, is because your framework is slightly weighted differently than mine. And maybe it's the fact that the weights are different, not the aspects of the energy system that we're arguing about. It's about how we value it. And that's the complexity, really, that we're having to deal with. So I'll leave you with this last thought, which I really loved from a 2012 edition of The Economist, which is really about take advantage of walk through the door when the door's open, let's put it that way. So I'll stop there. It's 2 after 6, and I think we have about 15 minutes for questions. So thanks for your attention, and look forward to questions.
Students first, please.
Hi, thank you for your presentation. So my question was, you showed the urgency for the need in increase of efficiency of carbon technologies, right? So where is this urgency expressed? Like, we had a talk recently where the presenter expressed that how the state legislatures is not ready to accept climate change. So, like, where is this urgency expressed?
So I would say that the urgency is understood from the climate science perspective, which is language that comes out from the IPCC about the need for decarbonization. And at some levels in decision making, it's expressed, for example, in the Cancun Accord that came forward from the UNFCCC, if all those acronyms make sense to you. But the challenge of implementing the goals or the desires there is, again, come back to that complexity diagram that I showed, because decisions around urgency are a trade-off relative to impact. And that's where you see, I'll call it, prudent, politically acceptable decisions move forward, which are toward the pathway, but may not be at the same rate of pace of change that the science might say. And so it's a mix.
Hi, thank you so much for the presentation. I'm here. So it was interesting that you mentioned in the end the shared asset business models. How do you think those can be included in your modeling scenarios? Would that reduce sort of the overall demand? Would that increase the efficiency of the way businesses and technologies function? How can that be accounted in the future?
Yeah, so if you look, I'll just use a single example here of transportation, right? Almost all transportation models think about GDP-driven vehicle miles traveled, and then an occupancy rate of the vehicle, and then the number of vehicles that are on the road in a single ownership model. So you can now calculate many different ways of thinking about how do you express a shared asset model in just transport. That's one example of that. You can think about households, you can think about hotels, you can think about all sorts of things, and how to capture those creatively in a model.
Hey, so thanks for your talk. I had a question relating to nuclear. I noticed on some of your slides as far as projections for the future that there was either a flat or a slight decrease in how nuclear contributes. So I was wondering if you could comment on, and you mentioned that part of it's due to the fact that not many nuclear facilities are being built. So I was wondering if you could comment on that and what you see as the future of like small modular reactors and those things kind of penetrating into normal people's households and things like that.
Yeah, good question. So the U.S. numbers that you saw on those projections assumed maybe an additional 20-year life extension of the existing fleet, but then in the economics calculation, that frankly the cost of nuclear would make it non-economic. So it's never a preferred choice to build out in the future in those scenarios with those assumptions. That's different in different countries right now. I mean, some countries have moratorium, others don't. The cost of nuclears right now is pretty prohibitive in most places around the world, depending on what the relative economics is of other options. Currently, if I remember the numbers correctly, there's approximately 65 gigawatts of nuclear planned or in construction. So, and that might come online between now and say 2025, and I'm not sure exactly, what that might look like in 5 years, right? There might be announced another hundreds of gigawatts or more, right? But today, if you think about it, you can plan on approximately most of that being built because it's in places that have committed to it, relative to annually more than 100 gigawatts of other clean energy or low carbon energies being built annually. So in those 20 years, you'd see, a pretty interesting change. Now, on the SMR side, at least in all of my understanding and working with the SMR community, they're not talking about wildly dispersive small reactors. They're talking about kind of more a manufacturing oriented of a reactor that might be around 10 or, well, not 10, but maybe hundreds of megawatts, and then you build out a facility of a gigawatt, but it's at a facility rather than go in and build one plant that's a gigawatt. And so it's still in an isolated area, controlled, protected area. So it's not distributed like your question supposed in terms of, around communities, et cetera. Those are still in design mode, and they've yet to really been penciled out economically for non-military operations. And so the answer's unknown, I think, at this stage, but hopeful.
Hi, my name is Brian Davis, right here, to your right.
Oh, I'm sorry.
Yeah.
I thought I was going back.
My question relates to what you were talking about earlier in terms of carbon emission reduction. And you were mentioning the need to drastically reduce energy demand levels across various sectors. My question is, how do you present that to players in the private sector as anything else other than a competitive disadvantage? Because it's really hard for me to imagine, especially with us being in a global economy, like you were discussing earlier, how private players might hear something like that and balk.
Which private players are you talking about? Utilities?
Yeah.
Yeah. So that comes to the couple of conversations earlier about the, fundamentally decreasing utility sales in terms of efficiency. So that's a utility perspective, but then you've got the other companies which are in there providing the energy services and the demand reduction. So ESCOs, others that are in providing demand response, et cetera. To them, that's a business opportunity. To a utility, it looks like, oh, you're decreasing my commodity sale. And the question then comes forward in terms of other pieces which I mentioned, which is how do you value the service which is provided, in this case, I'll just say by a delivered electron, right? So the classic example of value to all of us is our communication, right? We pay so much for these today, and we opt in to pay for it because it delivers value to us relative to, for example, the old wired telephone, if you ever lived in a household with an old wired telephone, that is. And that's a really different value proposition. So a lot of utility executives, actually those thinking on the front end of it, is how do I convert my business model from a commodity business model, delivering kilowatt hours, to delivering services? And what do those services look like and what do those pricing systems look like? Could I actually charge you for cold food, hair drying, air conditioning? And for those of you who are dealing with aggregated or disaggregated electricity information, frankly, in a smart censored house, you would know exactly what those loads are, and you could probably price those. But you can't right now. Go ahead.
So my question is, on one of your renewable energy slides, you had a lot of different things attached to it, and it seems like state by state, what people consider renewable is different. And you mentioned like carbon capture is not really a renewable energy, it could be a low carbon energy. Do you think that we need to come to an agreement about these sorts of definitions before we can really come to any agreements or move forward?
So states in the U.S. do have differing standards for what qualifies under their renewable portfolio standards. Different countries have slightly different ones as well. I would say ideally there would be common definitions or at least a common framework for definitions that would allow national trading or international trading of the qualities of those aspects. That's ideally. I don't think it's necessary, but I also think that people want more expression of their own values within their own environment. And so I would embrace kind of what's ideal and what's local, and you'll come to something in the middle. So I don't think it's necessary, but maybe desired. Yeah.
So my question refers to the slide that you presented that had in the kind of like lots of renewables and today's versus today's scenario, it showed energy production from coal natural gas combined cycle and natural gas combustion turbine. And I thought it was interesting that even in the case of coal, it kind of shifted to this ramping up and down pretty frequently sort of way of operating. But, we hear that it's a common notion that coal can't do that. It can only turn on and off, like, it takes 24 hours to turn on and off or something, and so it needs to be running at a constant rate. And we hear that a lot. And so my question is it technically possible for coal to do something like that, or is it just kind of economically not appealing today?
Great question, and the answer is yes, it's absolutely technically possible. I'd refer you to a case study we published under the 21st Century Power Partnership in association with a utility here in North America, where they actually converted their 1970s coal fleet into what they called super peakers, 95% peaking capacity, peaking capability, and they did it via operational changes, not really with a lot of capital. Of course, it has longevity impacts, it has operation and maintenance cost changes factor, but technically, you can do that even with an old fleet. Now, if you actually went in and started to rethink the metals in the system, et cetera, you could probably design a coal plant for ramping if you'd like to, but we haven't done that in the past. So the question really is, can we utilize this essentially asset base today without becoming stranded assets going forward in the future? And the answer is yes, if you chose to, if you could absorb the impacts of it, if there's an economic model to reward it. Yeah. Good question. Sorry, we're back here.
Firstly, I wanted to add to the already made comments that this was a wonderful presentation. I really appreciated it. I thought it was very informative, and I loved all the graphics especially. So I had, it's basically a two-part question. I wanted to go back to an early statement that you made that as people get older, they care about their kids and their grandkids. And then you mentioned a study that said that older people showed that characteristic. So I was wondering if that was controlling for the possibility that it was just a generational difference.
It was, so you can look at the work, I think it's under Easton Drury and Carolyn Davidson of NREL, so we did econometric analysis, particularly of PV system purchases in California.
Okay. So
That's
it is
one. There may be some other ones that Varun or Michael might know about as well. That's the one that I was thinking about in that quote.
Okay. And so I was wondering if I wanted to look a little more into the impact of that, and because to me it seems like there could be two competing effects of that, which is one that people are looking more into the future, so they may care more about renewables, and the opposite being that they want to look out economically for their descendants.
At least as I understood the questions that were asked and the data that came back, it was that they were concerned about the environment that they're leaving for their children and grandchildren. And there may be some aspect, I'm unclear in terms of the economic prosperity elements of it, but it was frankly across a pretty broad swath of economic sectors or segments. So it was really more about the environment underneath it. So.
Just one final question.
Yeah, thanks again for joining us. Excellent presentation, insightful. A couple quick questions. What do you think will happen as far as the morphing into the final clean power plan? And secondly, since you're doing econometric analysis, I haven't heard yet a good model, perhaps you have it, of how to value the hedge value of, say, a 20-year PPA for utility scale solar at 5 cents a kilowatt hour. And because from what I've heard, you can't really get gas hedges, much further than 5 or 7 years. And so it's difficult to understand, is it a blocked Black-Scholes or what, to fully assess the value of that fixed rate 20-year contract PPA and its hedging value. Maybe you've got some economic analysis on that.
So I don't think I'm going to comment on what I think the final plan might look like. It's probably not appropriate for us, but it will be likely some combination of those 4 building blocks and a fair amount of flexibility. There was a lot of misunderstanding about the options that were put out in the draft, about states being able to work together, states proposing different metrics, et cetera. And I think they received, 3 million comments, and there working hard on what that final rule might look like. To your other point in terms of how does one express the value of the fixed rate nature of a renewable plant, essentially. It's expressed in a couple of different ways right now, which is that that's actually amortized into a fixed income asset, and for many companies, or for a couple of companies that have actually figured that out, they're pooling fixed income assets and those with some variability into what's called a yield co. So it's essentially selling off the revenue streams going forward. It's the exact same thing Mid-American did with their investment in a big solar plant and wind plant, which is they actually went out to the bond market and said, this is a fixed income instrument. We're going to sell a bond based on that instrument and take it off our balance sheet and put it onto all of you. So that's where it's captured today. Frankly, it's not captured in the option value. We've talked about that. We've written lots of papers. Ryan Weiser and Mark Bollinger also have at Livermore. But the fact is that you can't get gas hedges out that far, and so you don't know your gas exposure out that far, means that you can't calculate it out that far. So, see, to that point.